In this video, we're going to take a quick look at Chapter 11 and discuss all of the things that you should have gotten from the reading, some old, some new. So anytime we have rolling as translational motion, we're going to consider objects that only roll smoothly, meaning that there's going to be no slipping with the wheel and the surface that it's rolling on. And we can say the center of the mass of the object moves in a line parallel to the surface, and objects rotate around their center of mass. So think of a wheel rotating about its center of mass, which would be in the center of that wheel. And the arc length that it rotates through, since there's no slipping, this arc length here is going to be equivalent to the translational distance. So we're going to call that S, and S is just theta times r, theta being the angle through which we rotate. And then from that, we can find that the velocity of the center of mass is omega times r, where omega is the angular velocity. Now, if we have pure rotational motion, as in picture A here, that means that at the outer rim, the tangential velocity is equal to the angular velocity times the radius. If we have pure translational motion, then they're all moving in the same direction, and they're all moving with the same velocity. So the velocity of the center of mass is the same as the tangential velocity. However, in rolling motion, the combination of rotational, translational, we know the velocity of the center of mass, because this is rolling, we're not moving at the point of contact because there is no slipping, and the translational velocity at the top is actually 2 times the center of velocity, or excuse me, the velocity of the center of mass. And so this allows us to answer this checkpoint question here, that A is the same and B is less than. We know that if objects are moving, they have energy, and if an object is rotating, it also has energy. So that means when something is moving translationally and rotationally, then the kinetic energy is going to be the combination of the two separate kinetic energies, where we have 1/2 I omega squared and 1/2 mv squared. Now the v here is going to be the velocity of the center of mass, because we look at that translationally. How is this object moving through space? If a wheel accelerates, its angular speed must be changing, and a force has to cause that change, and a force to cause that change and not slip is going to be static friction. And so the acceleration of the object, this is the linear acceleration, is going to equal alpha times r. Now that's talking about the center of mass. So this bike or the car is accelerating translationally equal to alpha times r. For smooth rolling down a ramp, we have a nice diagram here that shows why we are going to roll, because our point of contact is going to be down here at P, but gravity is slightly off of that. And so this is going to cause a rotation, or this torque is going to cause a rotation, and therefore this is going to begin to rotate and roll down the hill. This equation right here, equation 1110, is a nice new little simplification that we did not use in AP Physics 1. And this allows us, when we have something rolling down a hill, so this is just for something rolling down a hill, we can find its acceleration down the hill by using this formula, where we have g sine theta divided by 1 plus the moment of inertia divided by mr squared. Okay? And so this is a little new. It kind of figures in the kinetic energy both linearly and rotationally. Something to note here is that friction is causing the rotation. It's part of the rotation, the fact that the center of mass is over its support and friction is allowing it not to slip. Then we are going to see the torque and the rotation. Without friction, the object would simply slide down the ramp. Yo-yos are a fun little toy, but they also include a lot of physics. And so as a yo-yo moves down a string, it's losing its potential energy, which we can find by mgh, but it gains rotational and translational energy. So that energy is being split into two different types, rotational and translational. And so to find the linear acceleration of a yo-yo, we can just assume that, well, this is a yo-yo that's going down a ramp. It's just rolling at an angle of 90 degrees. The difference here is that it rolls on an axle instead of its outer surface, and it's slowed by tension rather than friction. And so we can use the result of equation 1110 to calculate the acceleration of a yo-yo as it falls. And we notice this when we throw a yo-yo down, or if we just drop a yo-yo, we see that its acceleration it's much smaller than just dropping an object. And so say we have a 150-gram yo-yo with an inner radius of 3 millimeters, and its moment of inertia is 3 times 10 to the negative fifth kilogram meter squared. So we can find the acceleration by plugging into this equation, that we get a negative 0.4 meters per second squared, much, much less than baby g. So previously we defined torque as the force times the lever arm, and maybe even threw in sine theta in there if we had an angle between them. And we defined it only for rotating body and a fixed axis. Now we redefine it for an individual particle that moves along any path relative to a fixed point. So it doesn't need to be a circle. And what that does is that turns torque into a vector. And so the direction of this torque can now be determined with the right-hand rule. And this is actually using the right-hand rule from cross products that we did way back at the beginning of the semester. And so this defines torque as R cross F. Now this is important. It matters which one we cross with which. Knowing cross products, remembering cross products, the order is particular. So it's the displacement, or the position vector, I should say, not just the displacement, but the radius vector, the distance from our axis of rotation, that vector, that position vector, cross the force vector. And if we know the magnitudes and the angle between them, we can simplify it to RF sine theta. Or we can say it's R times the perpendicular F, or the perpendicular R times F. That's basically what we did back in AP Physics 1. But now we're going to look at the general case where we have two vectors and we can find the torque vector through a cross product. Take a look at this checkpoint, pause the video, read over the answers. This diagram here shows a few examples of calculating torque and using the right-hand rule to find the direction. This diagram can be a little confusing, so we're going to look at some examples in class that may be able to help you. But if you can, follow along with this diagram and move your hands to see, so you can determine the direction of the torque. Now, one thing to keep in mind here, anytime we want to find the cross product, we're always looking at the angle that's less than 180. So we're putting our fingers along R here, and we're crossing them, or we're curling them to our force. And so in order to, with our right hand on this one, our thumb has to be into the screen, and so that gives us the direction of the torque. And so if there's linear momentum and an object is rotating, then there's going to be angular momentum. And we're going to redefine angular momentum, and we're going to use L as the vector. And it is a vector, and the angular momentum is going to equal the cross product of the position vector with the translational momentum vector. Okay, so we'd have to look at the momentum of the object, the linear momentum, and take the position cross that momentum vector. And well, what is this momentum vector? The momentum vector is just m times the velocity vector. So really what we're doing here is we're taking m times the cross product of the position vector with the velocity vector. Just like with any cross product, we use the right-hand rule to determine the direction, and we can simplify if we have the angle between the position vector and the velocity vector. If we have that angle phi, then we can just take RMV sine phi. Or if we have the perpendicular components, we can multiply those as well. Because of the right-hand rule, the momentum, the angular momentum, is always perpendicular to the plane formed by the position and linear momentum vectors. If you recall back to when we talked about momentum, we redefined Newton's second law by saying that the net force was equal to the derivative of the momentum with respect to time. Well, now we can do the same thing angularly and say that the net torque, that vector, is equal to the derivative of the angular momentum with respect to time. In order for this to work, the torque and the angular momentum must be defined with respect to the same point. Typically, we pick the origin for this. And this all stems back to this equation that we had back in momentum. Checkpoint 5 here is a good one to take a look at to just review a few things conceptually. Now, in those previous slides, these little L's that I was talking about here were all about a single particle. So this was looking at single particles in a system. So just like with the moment of inertia, we can sum up all of the little particles' mass times the radius squared to get the total moment of inertia of the object. We can do the same thing with the angular momenta. If we sum up all of the angular momenta, or use this sum here, and this is more of a theoretical sum, not that we're physically going to do this, but just the idea of summing up all of those tiny little momenta, we get the big L momentum, which is our total angular momentum of an object. And so the derivative of that with respect of time, or the rate of change of this net angular momentum, is going to be the sum of the net torque on the entire object, or in other words, the net torque on the entire object, the whole rigid body, is going to equal the derivative of the total angular momentum. And you might think that this is a little repetitive from what was stated before, which it is and it isn't, in that it is the same relationship, and that's important, that the torque on an object is going to equal the rate of change of the momentum of that object. But now this is talking about, instead of just a particle, it's the entire object, the entire body itself. And so using the same logic, and I'm going to go through this here very quickly, if we look at the angular momentum and we're going to add up the little tiny momenta of each particle, well, we know we define that as the mass times the velocity times the position vector. And if we're just looking at the perpendicular portion, we know that omega times r is our v, and then we get an mr squared, and the sum of mr squared we know gives us our moment of inertia of the body. So this simplifies for us to say that, okay, the angular momentum of an object that is fixed at an axis is just simply going to be I omega. And this should make a little intuitive sense in that I, well, that's kind of like a mass, and omega is kind of like a velocity, and so momentum is mass times velocity. So angular momentum is angular mass times angular velocity. Now this table 11.1 is very important in that it gives us the relationships between our translational objects, or our translational formulas, and our rotational formulas. Just like before, when we have momentum, we know that the law of conservation of momentum exists. Well, that occurs in translational momentum, and it occurs in angular momentum. Now, the key thing here is they are conserved separately. Angular momentum and rotational momentum are conserved separately. They do not, we don't exchange from one to the other. And if you think back in AP Physics 1, we watched that video of the bullet shooting into a block and shooting up into the air. That kind of illustrates that angular momentum and linear momentum are conserved separately. Now, when we have the conservation of angular momentum, basically we're going to see that the initial momentum is equal to the final momentum. So I alpha initial is going to equal I alpha final. And we've seen all of these experiments before of showing the conservation of angular momentum when we are spinning and we pull our arms in because we're changing our moment of inertia. It's changing the rate at which we rotate. Well, this can be seen in a student spinning on a stool, a springboard diver, or a long jumper, all of those conserving their angular momentum by changing the moment of inertia, and in turn the angular velocity has to change. Take a look at checkpoint 7 here, talking about a rhinoceros beetle, and see if you can get these answers. The last thing here in chapter 11 is talking about the precession of a gyroscope, and we're going to look at this more conceptually than anything. But basically, a spinning gyroscope, and you've seen demonstrations of this. You've seen the spinning wheel in class where you can hold it up, and so the reason that this works is because of the conservation of angular momentum. And so when we have something that's spinning, there is angular momentum, and it's very hard to change that, and that momentum wants to be conserved. And only torque can change the angular momentum, so an outside force is what can change it. And without that outside force, it's going to continue on forever. And there is this one equation that comes up. We're not going to use it a whole lot, but it's talking about the precession rate, and we use capital omega here. and that's when we have the mass times baby g times r divided by I omega. So you can see a few things in here. Well, we've got mgr and we have I omega, the I omega being our momentum. Now, this is true for something that is spinning pretty fast. If you're spinning slowly, then there's not a whole lot of angular momentum, so this doesn't really work all that well. Now, notice this point here. This precession rate is actually independent of mass. And you might say, well, how is it independent of mass? There's m right there in the equation. Well, yes, there is. There's an m in the numerator. However, I in the denominator is also proportional to m. It's dependent upon m. So those m's cancel. Now, we leave it there just in case we have it in terms of m and I, depending upon the given information, depending on, if you have the momentum or if you have the moment of inertia, so on and so forth. But however, the mass does not matter, but g does. So it does matter what planet we're on, it just doesn't matter the mass of the object. So I know I flew through things pretty quickly there, but I want to try to get all chapter 11 into one cohesive video. And these last two slides here are a nice summary of all of the equations that we would need to have ready for the test.